Hello everyone, welcome to this Transit Data Session 5C. I see the numbers of participants are still going up, but I think we can start with our short introduction. Thank you all for attending this session. My name is Menno. I'm working as researcher for the Smart Public Transport Lab of the TU Delft in the Netherlands, and I'm also working as public transport modeler for Transport for London in the UK. It's my pleasure to moderate this session. So today we will have 5 very interesting presentations with a focus of data applications for rail. And I guess we have very interestingly presentations from the US, from Canada, from the UK. So even though we're not really able to travel a lot, hopefully this gives us a sort of quick tour around the world with most recent insights. A sort of general things which you're probably already aware of. Each presenter has 6 minutes to present. There is not really a Q&A directly after the presentation. You can use the link in the Google Docs form for that. However, if we have a couple of minutes at the end of the session and you have any urgent questions, feel free to pop them in the chat, and we can see if the speaker can answer some questions maybe directly. If you do that, it's probably handy to refer to the name of the speaker or the presentation title so we know who has to answer the question. As you also know, the presentations will be recorded. And I guess without further ado, let me introduce as a first speaker, Michael from WMATA. You want to share your screen, Michael?
Sure thing. Good morning, everyone. And I assume you can see everything?
Yes, looks all good.
Great. Great. Thank you for the opportunity for me to present today. This is what I've been focused on mainly over the last year or so, and I'm excited to share and get some feedback. Just a little background. WMATA in Washington, D.C., we operate Metro Rail. It has 91 stations, and it's a 2-track system, so in and out with 3 trunks. We interline 3 lines, 3 colors on one line, 2 on another, and a single red line. When an incident happens on the rail system, there's not a lot of alternatives. We can sometimes single track around it, but in general, we are challenged to provide quality service to our customers because of the nature of the 2-track system on the rail line. Back in 2016, we launched a new metric of customer-focused on-time performance, which really looks at the customer's tap-in and tap-out times. We're lucky to have a dual-tap distance-based fare system, and that allows us to have thresholds for when a customer's on time. More than that, they're late. And we use that now as our primary on-time performance metric for rail. In 2018, we launched a reliability, customer reliability program called Rush Hour Promise. If your trip was more than 15 minutes beyond that threshold, you got a credit for your trip fare. And in 2019, we reduced that 15 to 10 minutes. That prompted us as an agency, with all of these different metrics for our customer on-time performance, and now actually paying a bill monthly. Like, well, we wanted to know, well, what was the cause of these delays, and can we pin them down and focus in on making some changes that could help reduce the customer delays and also reduce the impact to our pockets. So I developed an algorithm that basically tries to answer this question, and this is a lot of stuff on the screen. And interestingly, like, we're merging a lot of different data sources together to try to answer this question. But the primary answer to the question is that we are using data from the schedule and from the train movements and the customer movements together through a process called a model we have called TRACE, which is an ODX, origin, destination, and interchange transfer model that allows us to link our customer movements to our rail movements. And those allow us to attribute late customers to late trains. We then link our late train stops to one another to identify zones of lateness, and then look within that zone of lateness for any trains that have been flagged as having a trouble ticket that explains why they're late. So once we get across this sort of hard boundary between the rail system data, ODX, and then the incident system, once we cross over that boundary with this ticket match, then we can then follow through the ticket structure into work orders and assets to really identify what piece failed and how that failure in either the hardware or an operating environment impacted our customers. So just to give you another picture of how this all works, imagine here that we have a series of trains that are moving through the system. This is a time-space diagram. Trains are moving from kind of top to bottom and from left to right. The first two trains get through on time. The third train moves along and then it stops and it sits there for a while and then it continues on. The trains behind it queue up behind that train and they create a zone of lateness. And we can identify the zone of lateness by the train movements. We can see that the trains are not hitting the stations on time, but we can also identify the zone of lateness by seeing where customers are exiting late. And we know that if a customer is exiting late, they're probably exiting a late train, and then we can add those train stops to the zone. Then we create this zone of lateness basically, and we scan through it looking for tickets that describe why a train was late. Unfortunately, we don't have a system in place where we write a ticket for every late train. So we have to find one that has a ticket describing it. And sometimes the ticket describes another ticket. So we have to follow along these trail of tickets to identify what the root cause of the problem was. So I've got an example here that shows how this all works, but you can see we start off with these train paths, right? And in this diagram, the paths of the train are blue while the train is on time. And then when the train goes to late, it turns red. And you can start to see these zones forming, and you can sort of figure that probably the incident occurred kind of right up here in the upper right-hand corner of this one plot, because that's when the trains started going from on time to late. Transforming those into train stops, we can see we've got these bubbles here of late customers. We can really see that the customers are exiting the system late, and it's probably creating this zone. They're all probably late for the same reason. And then the third one, we really start to get down to an incident time-space zone where basically we identify zones of lateness. And if a train made it through on time, that separates one lateness zone from another one, creating a boundary between the zones. And we can then sum up all of the total customer delay associated with these zones in order to attribute total customer delay and total rush hour promise credits given back to the customers linked to the ticket that was associated with the zone. I have one example here. One example here to show you kind of what it can look like. The one additional thing is that when a train has a ticket describing why it's late, the line turns yellow. So you can see here, this was a pair of mornings where we had two different operational alternatives to a similar approach. One we did cranking and clamping around a switch, and the other one we single tracked around it, but reduced our throughput. And you can see here that the one morning on February 7th caused a lot of delay throughout the rail system throughout the morning. And if we flip over to the other view of the late customers, we can see that the one on the left really had a much stronger impact on our customers, whereas the one on the right didn't. So this allows us to estimate how we might better handle operational issues as well as maintenance issues. So to summarize, we're creating zones of lateness, linking those zones of lateness to customers and to tickets. We're trying to get smarter about our zones, start handling overlapping zones, going from a binary late, not late, to a sort of a lateness. And then really linking this data into rail performance, capital program, and also performance management. Thanks.
Thank you, Michael. I think that's very interesting and a very relevant topic to look at. If I would like to give the floor to our second presenter, Zen Hong from McGill. Could you please share your screen and unmute?
Hi, everyone. Can you see my screen?
Yes, it looks so good.
Okay. Hello, today I want to introduce how to incorporate travel behavior regularity into passenger flow forecasting. We all know that passenger flow forecasting is very important in a metro system. For example, we can use it for crowding management or service scheduling, especially in the case we can have an accurate multi-step forecast. In this figure, I show some traditional method in passenger flow forecast. In traditional method, we modeled it as a time series problem, where we use historical data to learn the model, and after learning the model, we use the model to do the forecast. All we know about the passenger flow is the aggregated count data. But in this work, we want to show that travel behavior regularity also plays a very important role in passenger flow forecasting. But this is often ignored in traditional method. And to illustrate that, here I show trip chain of a passenger in metro system. In a metro system, if a passenger come to a place by metro, and after certain activities, they probably will also return by metro. You also use metro in their returning trip. And as shown in this come and return circle, we know that the destination of this trip is often the same as the origin station of their next trip. And this come and return circle is very prevalent in our case. I think it's very prevalent in most of the metro system. In Guangzhou metro system, we found that this type of trip makes up around 60% in all the trips. And more importantly, for certain activities such as work or home, the come and return time are highly regular, and that inspires us to build a model to learn relationship between the alighting flow and the boarding flow, and use this relationship to better forecast the boarding flow in the future. And to do so, we use two tools. One is the returning flow, and the other is the returning probability parallelogram, as shown in this figure. In this figure, the left panel is the alighting flow at metro station S, and the alighting flow represents the number of passengers who have come to this station. And after doing certain activities, the upper panel shows the number of boardings for this part of passenger in their next trip. And we refer to this type of boarding as the returning flow. In the middle is the returning probability parallelogram, in short, the RPP. Each row of the RPP represents the probability of returning given a certain alighting time. And in this figure, we can see for this station, there are very high alighting flow at around 8 a.m. in the morning. And most of this part of passenger will return at around 16 p.m. in the afternoon. And the RPP, we assume it is very regular. Therefore, we can estimate the RPP from the historical data, and we assume it is unchanged over time. And also, the RPP encodes the long-term dependency in the alighting flow and the returning flow. And therefore, for example, in this station, the alighting flow in the morning can dominate the returning flow in the afternoon. And we also found that the returning flow takes up a very, very high percentage in the all boarding flow. Therefore, we can assume that using the returning flow can better forecast the boarding flow. And we can also use the RPP to estimate the returning flow in the future, as shown in this equation. But I will not discuss it in this short presentation. But here, I want to show that in this page, I show the real boarding flow and our estimated returning flow. We can find that they are highly correlated, and especially as pointed out by the red arrow, the returning flow can even reflect some unusual fluctuation of the boarding flow, and this is very hard to be predicted by normal method. And we did some experiment. We used the S-ARIMA as our baseline forecasting model, and we used the returning flow as the external covariate, and to inject into the S-ARIMA model to form another type of forecast. Then we do the experiment. To quantify the effect of the returning flow, we use the difference in the SMAP arrow. If the difference is negative, it means our method can help the forecast. And we do this for all the stations. And here's the result. And we can find for most of the stations, the difference is negative, which means the returning flow improved the forecast. And
1 minute to go.
cluster the stations by their RPP, and we can find for cluster 1, this is the commercial areas, the returning flow can better help the boarding flow forecast. And for more applications, we found the RPP and this travel behavior-based forecast can better help us to predict the boarding flow in some anomaly events. And it can also help for in the multi-step forecast. In the future, we want to extend it to a tap-in only system, and maybe can apply it to other time series model or other transportation mode. And for more information, please refer to the long presentation or the 4 papers. And thank you.
Thank you very much. That was very interesting as well. Can I ask Said as our third speaker to please share your screen and unmute?
Sure. Can you hear me okay?
Yes, that's all good.
All right. Hello, everybody. I am Said Saidi, assistant professor at the Department of Civil Engineering at the University of Calgary. Before joining University of Calgary, I was a postdoctoral associate at MIT Transit Lab. And today I'm presenting a very brief overview of one of the projects I worked on at MIT, working with professors Nigel Wilson, Harris Koutsopoulos, and Jinhua Zhao on mesoscopic modeling of train operations using empirical data. To begin with, let's look at 1 hour of operation on MBTA red line. This is during the PM peak period. This is the trajectories of trains, and pretty much the operations is smooth. However, on the same time period but a different day, we see that an initial train disruption has affected several following trains after, just similar to the example that you saw in Michael's presentation. This type of incidents or interruptions are pretty common, especially in older systems. And the shape of this delay propagation really depends on initial conditions. What are the dispatched headways? Where are the locations of that initial disruption? The duration of that, and even the dwell times or the demand in the system. So the motivation of this study is to develop a train operations model from the empirical data on a mesoscopic level. There are very accurate micro simulation models already developed, but this mesoscopic model is not as time and resource intensive as micro simulation models. At the same time, it provides richer and more accurate predictions than analytical models. However, the limitation with this model is that we're dealing with existing rolling stocks and signaling system because everything is based on the historical data. We're dealing with a fixed block signaling system. So if we have this following train K, far enough from its leader, the train will receive its maximum speed code and there will be no delay. However, if this train is within the influence zone of the leader, it will receive a slower speed code, and that's where we observe delays. So we can derive the train delay function on each block, which is based on the estimation of induced delay for a train that is closely following its leader. And we can see this type of delay region on the blocks that are before the stations. And this delay is really a function of the headway of the train K with respect to its previous train, and the delay of the previous train on the same block, and the dwell time of the previous train. And the shape of this curve really varies by blocks. That depends on the speed codes, lengths of blocks, or train specifications. So by sequentially applying this train delay functions on all the blocks, given some initial conditions, which is the trajectories of initial train, the dispatch headways, and also using a simple dwell time model using the AFC data, we can generate the trajectories of the following trains. Going back to the example I showed, the real example I showed in my first slide, we can generate the same scenario. So if we have a one-time 60-second interruption of a train at a bottleneck station, in this case, Park Street, we can see how following trains been affected because of that initial interruptions. And we can clearly see this delay propagation happening using this mesoscopic model. Another application which I wanted to mention is looking at the trade-off between the line throughput and delay per train. Again, in the case of MBTA red line, if we decrease the headway, peak hour headway from 4-minute to 3-minute headway, we see that the line throughput would increase up to a certain level though, but even that is at the expense of major delays to two trains. So exploring that effective capacity is another application of this model. I will just mention two more applications of this model. One, looking at headway regularity. So using this model, we can clearly see the impact of consistent headways on improving the line performance. And we can also look at different response strategies to the disruptions and explore different options, such as holding, dwell time control, or dropping a service. And I want to emphasize that really this model can be used both for offline applications and real time, after collecting all those historical data and generate those train delay curves. We can run the model in a simple spreadsheet model, so it has real-time applications. Thank you very much for your attention.
Thank you. Can I then invite Taku from UCL to unmute and share the screen? Screen is all there.
Okay, are you?
Yeah, we can hear you and see the screen, so it looks all good.
Screen. Okay, good. Okay. So you can see the screen. Okay. So thank you very much. Today I'm going to talk about investigating train dwell time using a signal bus level signal bus data. So understanding and predicting dwell time, it is very important. It's important not just for the train service planning, but also real-time railway traffic control. For example, if you have these situations, imagine that this is a junction, flat junction, and so which train should go fast? So maybe some trains are stopping at a platform. So kind of predicting dwell time is a very important element for traffic control. And then, so we have seen a lot of research on dwell time, and probably, most research is suggesting that the numbers of passengers may be one factor. So, in the future, it might be possible for traffic control systems to talk to such as, let's say, passenger number count systems like ticket buyer data. But currently, it's not yet done. But one thing I want to say here is that traffic management systems are basically the kind of safety critical systems. So we don't want to, increase the interface with other data systems for all sorts of the reasons. So in this research, we focus on the signal block or signal bus data. So what is it? So basically, you may have seen this kind of a system where a train is moving, and you can see that okay, now this signal block is occupied by a particular train. So the system basically records the time when a train enters a block with the station. For example, in this case, when this train enters this block, it records a timestamp. And then when maybe this train leaves, stop after stopping station, leaves this block and enters the next stop, next block, then it also records the time. So you can see that this is not exactly the same as the dwell time. I mean, if you define the dwell time as a such a time between the train stops and the train departs, so it's not the same as that dwell time. However, this is what the traffic management systems, which will be overlaid on a signal system, will see. And hence, the advantage is that for if you use this data, we don't need to access to the, let's say, signal passenger count data systems. So this research, so we are now looking into some particular line of the London suburban railway network. So this is a central London, and there's a line from Liverpool Street to a suburb. So we are looking into this signal bus level data from this same field to this line. So it's a sort of the line basically in a peak, picking up many passengers, and then many people get off at this station, Stratford, to change to the underground system, and then train itself continues to the Liverpool Street. So we are analyzing the sort of the AM peak service headway 10 minutes, but also kind of all day, including AM peak. So roughly around 100 services per day. And the data we have is 29th of April to the 21st of November. So in terms of technique, we use a Bayesian network. So basically, Bayesian network is a sort of the kind of the technique based on sort of the conditional probability. I mean, I wouldn't get into the details of this is a theory because this is not a sort of the method lecture. But basically, the idea is that if you stop at one station, it sort of update the probability of the dwell time of the next stop, for example. And so we use this technique. And in particular, this presentation, we use structural learning technique for this. So basically, what is it? If you have a lot of independent variables, you can see the sort of the dependence between these independent variables. So
1 minute to go.
Yeah, here is a result. We have a sort of peak only. This is sort of the identified structure. So basically, arrows mean the sort of the data dependency, and so Brentwood to the Stratford. So you can see that the M peak, its structure is quite simple, whereas all day you have a complicated structure. That maybe because the data is much more, and maybe there are many things out there. But interestingly, if you look at compare the M peak structure with the origin demand matrix, you can see quite interesting things. So as I said, Stratford is sort of alighting stations, and the people pick up, trains pick up stations from the upstream before the Stratford. You'd notice that the Ilford is actually the station where quite many people get on, but this is not reflected in this, this structure. So it seems that the point here is that this data dependence is not so kind of relevant. I mean, doesn't have a much relationship with the OD matrix. There are some other things are included in this model. So the concluding mark, so the signal bus data is not the same as the sort of vehicle system data, but it's useful for the traffic management purposes. And the sort of data, this data is affected by many factors, probably non-passenger factors, for example, driver tendency. Yeah, and maybe this is interesting data and can capture something which are not captured by some traditional passenger number models. That's it. Thank you.
Thank you, Taku. Jeremy, could I give you the floor for the last presentation of this session?
Certainly. This is a 12-minute presentation, so I'm going to speak at twice the speed.
Good, it's all visible.
All right. Okay, perfect. So my name is Jeremy Foran. I'm with BAI Communications. I've worked in the transit industry for about 10 years, primarily connected trains. I've been with BAI for about 5 years, and I lead the data analytics team here in Toronto. So I'm just going to walk you through who we are, what we do, and provide an example of a solution that we built for the TTC, the local subway operator here in Toronto. So it might feel fairly quick-paced. So BAI Communications is a global company. As a leading communications infrastructure provider, we deliver neutral host solutions that enrich lives by connecting communities and advancing economies. We're in 3 sectors: broadcast, neutral host, and 5G, transit and safety. In Toronto, BAI owns and operates the infrastructure that provides the public-facing Wi-Fi and carrier-agnostic DAS system. The idea here is that once you've built the infrastructure to provide the wireless connectivity in the subway, any additional services are complementary and, as a result, very cost-effective. So you can see here, there's a lot of revenue opportunities and applications, all utilizing a single backbone fiber infrastructure. Here in Toronto, we started wireless connectivity in 2015, and over the past 5 years expanded to a few other various services. So for example, we provide the connectivity to all the digital signage at the platform level. If you tap your Presto card for the fare card payment, that goes over our DIM fiber. And currently we have a lot of POCs on the go to test and deliver things like video analytics, environmental monitoring, and asset tracking. So I want to take you through one of the problems that we're using the Wi-Fi to solve. If you travel in any of these, major subway systems, you're aware of the problem of overcrowding. It's inconvenient. There's little or no space to move, and boarding and disembarking from the train becomes challenging. In terms of safety, once a platform has become overcrowded, it becomes difficult to evacuate the stations in the case of emergency. Typically, the safety staff are monitoring hundreds or even thousands of camera feeds to try and identify places where crowding may be occurring. And in an environment where people are constantly moving, this becomes even more challenging to find these sort of emerging issues. So we looked at the Wi-Fi data to see how it correlates to how people enter and exit the stations. We found a 0.9 correlation, which is what we needed to prove as the basis of detecting this overcrowding using the Wi-Fi. So this is what the Wi-Fi data looks like for a particular station. So this is the associations to all of the access points, how many devices are associated to all of the access points in a single station. And you can see clearly when the day starts, the morning rush, the evening rush, and then the end of service. Here is what that data looks like when you zoom in. You might notice it was pretty spiky. When a train is coming into the station, all of the devices that are in the people's hands or even in their pockets are trying to associate to Wi-Fi. So as the train enters the station and the signal becomes available, they connect, and as a result, we see those connections rise and then drop when the train leaves. Sometimes we even have 2 trains coming at the same time. So detecting overcrowding isn't just about detecting thresholds, but when the pattern changes from that spiky to something else. So this is what it looks like when we have overcrowding starting to happen, and we can see that here with a notification that went out. By looking at this data, we can see how long these sort of disruptions occurred at a particular station, and then how it propagated out across the network. We then take all of that information. We have a serverless architecture, so all of that data is being pumped to the cloud, where we have various business logic models that run for each and individual station, and push that out to another database that maintains the state of the station as it relates to crowding or overcrowding. We then publish that in a dashboard. That dashboard makes it a lot easier for that safety staff now to get indications or hints of where they might want to focus their attention to try and hone in on places that might be suffering from overcrowding. We also have started looking at this for addressing COVID concerns. So making this data publicly available so that people can see how easy it would be to observe social distancing at any particular station. This is based on real-time information and also forecasting information. That's it for me. How is that? A little under time?
It's perfectly in time, 5 minutes and a few seconds.
Perfect.
Thank you. So if anyone from the audience has any urgent questions, feel free to pop them in the Q&A so we can have a go at them directly, because we still have some time left. In the meantime, I have a few questions as well myself, so I will just start with that, and hopefully others will add to that. If I may start with the first presentation by Michael. I think it's a very interesting approach to connect the incidents with passenger delays. I was curious how you deal, or how you potentially deal in future developments with interactions between incidents. So typically, if you have many incidents maybe happening around the same time or same location, is it possible to sort of separate them?
Yeah, we're hoping to move towards a almost like a topographical model, where you can imagine, instead of it being, you know, on time or late, you can imagine there's like variation in lateness. And then if you could have potentially like one kind of mountain of lateness, and then another kind of hill of lateness kind of runs up to it, and then they boost, that you can actually be able to disaggregate the lateness from one event and the lateness from another event. And really trying to start thinking of it, you know, using different models, different mind models, to try to figure out how we can sort of start to interpret that. So yeah, again, like as we move away from a not late to lateness, we may be able to untangle overlapping delays.
Great, thanks. So I just have a question for each presentation, but all other presenters feel free to add other questions or add some discussion when appropriate. For the second presentation, I was curious if you see any differences in sort of performance between different areas or different time periods, because I could imagine that regularity is more obvious in peaks or at areas with a high commuter proportion, whilst maybe at areas with more tourists or on a Saturday, you see different patterns. I was wondering if you could see any performance difference.
Okay, very, very good question. In our experiments, we compared different stations, and we found that for the commercial type stations, for people coming in the morning and they return in the afternoon or in the evening, and we found that this is our method is more helpful and can provide a more accurate forecasting. But for other areas, such as the residential area, people come to their home in the evening, and they reuse the metro in tomorrow, and this type is not as good as the commercial areas. Nice question. Apparently, there are some patterns for different areas. For certain stations, our methods can help more. Yes. Thank you.
Thanks. So for the third presentation, Said, what I really liked is that you I've seen quite some mesoscopic models focusing on more urban systems, I guess, but I found very interesting to see a mesoscopic model incorporating a signaling system as well. I was curious to what extent your model might be able to incorporate passengers as well. Is it really a train movement model, or can it incorporate passenger loads or behavior to maybe better quantify disruption impacts in the future?
Yeah, very good question. Yeah, so far the main focus is on train modeling. We're just using a simple, not too simple, but dual-time model that takes into account the number of passenger activities, and that component this time is based on the historical AFC data. So assuming that we have the real-time OD demand, then we can improve that part of the model as well. But again, we're not really focusing to too much detail here. What is the exact train load and detailed very sophisticated dual-time model, not in a mesoscopic model. So that's really the advantage of this model, is that it can run very fast, very quick. But if you want to look at more details, probably a micro simulation model would be a best.
That makes sense. Thanks. So for the fourth presentation, sorry, Taku, I was I think it's very interesting to see a sort of different approach, taking passengers sort of out of the equation and still be able to estimate dwell times. I was curious, did you have any sort of comparison or validation with a more detailed passenger dwell time model to see how far you're off with your sort of faster approach, or is it very accurate?
Yeah, so we haven't yet reached that stage, but I mean, there are sort of the anecdotal evidence, and there's also one paper. But yeah, so what we know is that I mean, actually, yeah, if you just focus on dwell time, I mean, train stops and then train departs, there might be good correlation. But yeah, some other factors are involved, and the railways are basically complicated systems. And, yeah, so the interesting challenge that how you sort of model some other bits.
Right, great, thanks. So Jeremy, I like the introduction of Wi-Fi here, but I think we've seen a lot of train models or passenger data, and I think we didn't have Wi-Fi in the session yet, so that's great to see. I was curious, as a sort of, I think it's very relevant, especially in these COVID times, to identify potential overcrowding. I was curious if you would also see applications, for example, using Wi-Fi to calibrate route choice models, for example, or that you can see how passengers move between the gates of a station?
Yeah, absolutely. So what we essentially do is check the MAC address of the device, and as it associates from access point to access point, we can see them transit through a station and then through the train network. And that does a really good job of providing us origin destination. We're looking to build this as a real-time sort of solution, so you can see people in flight. But there's obviously a lot of work that needs to be done there around privacy and hashing of the MAC addresses and all that kind of stuff. But also too, we have a lot of data, and we'd love to make it available to anyone who's interested in aiding a model or anything to that effect. So you can reach out to me.
Great, thanks. See if any of the other presenters might have questions for anyone else in the group. If it's silence, take that as a no. And I don't see any other Q&A as well, so I think if no one else has a question, we're at the end of the session then.
There's one question, I think, in the Q&A box there for Saeid. I don't know if you can see it.
Yes, that's right.
Or did we address that already?
Yeah, I think we addressed it, but
Perfect.
yeah, okay. Yeah, that one is addressed, so this should be fine. Well, if no one else has any other questions, then I would like to thank you all, and especially all the presenters, for the interesting work, and enjoy the rest of this conference.
Thank you.
Thank you very much. Yeah, thank you for chairing this session.